Well, we're back to finishing the review. And in this section, each polynomial function is factored, and I'm interested in you finding the degree and all of the zeros, specifically knowing the difference between real zeros and complex zeros. And for number 8, for f of x, the leading coefficient, if we were to multiply all of this together, we would eventually multiply x times x times x times x squared. And that would give us 1, 2, 3, 4, 5. So this would be a fifth degree polynomial function. And here we've got all of the factors. And now for each factor, we'll be able to find a zero or zeros. So in this case, for zeros, we would need to have x equals 0 or negative 2 or 5, and in this case 7, and since it's squared, that would be a double 7. So we have 1, 2, 3, 4, 5. There are our 5 zeros, and they're all real numbers, so that means that there would be no complex zeros. Okay, for this one, we have got 3 factors, and if we were to multiply and distribute all of this and expand it, we would multiply x squared times x squared, which would also be x to the fifth, so it's a fifth degree polynomial function. And now if we look at the zero or zeros of each factor, the middle one's the easiest. In this case, x would just be 5. And over here for the first one, to make x squared minus 7 equal 0, that means x squared would have to be 7, and x would have to be a positive or negative 7. And in the last case, for x squared plus 9 to equal 0, x squared would have to be equal to negative 9, and if we take the square root of both sides, x would be a positive or negative square root of negative 9, which is a positive or negative 3i. So we have real zeros of 5 and positive square root of 7, negative square root of 7. And then we have 2 complex zeros of 3i and negative 3i. Now for this last one, we don't know the equation, but we've got a table of values. And we had several questions, and I would first like to do numbers 10, 11, and 15, and then we'll look at the other ones in a moment. So first of all, for the y-intercept, you know that for any graph to intersect the y-axis, any point on the y-axis, x has to equal 0. So for the y-intercept, we're looking for where x equals 0, and there we have it. I usually say the y-intercept is negative 25. I've noticed some students like to say, give the actual coordinate points of 0, negative 25. And for number 11, for the x-intercepts, you know that any point on the x-axis, we have to have y equal to 0. So if we look at these values, we've got 3 places for which y equals 0. So the x-intercepts would be negative 3, 1, and 5. Now for number 15, we want a solution to this equation f of x equals 0, which is another way of just saying y equals 0. So where on earth does y equal 0? Well, that is just what we looked at for the problem before. There are 3 places where y equals 0, so you could give, for any solution, you could say it's negative 3, 1, or 5. Now, before we do problems 12, 13, and 14, what I'd like to do, and this is not on your review sheet, what I'd like to look at is one example here. We're not proving anything, but we're just noticing what's happening. And I've just made up a function here, f of x. And if you notice this array of values, we could be doing this operation right here, which I'm sure most of you are thinking of as synthetic division. So I'm going to go through the motions for both of these. And what I'd like to point out here is that we oftentimes call this synthetic division. And if we do refer to both of these processes here as synthetic division, what we've shown on the left here is that when f of x is divided by x plus 3, we get 5x squared minus 7x plus 2 with a remainder of 0. And on the right, if we also call this synthetic division, what we've shown is that f of x divided by x minus 2 equals 5x squared plus 18x plus 17 with a remainder of 40. Now the thing is, we could also look at both of these little schematics here, I guess I could call them. There's something else that it shows. If we call this process synthetic substitution, once again, it's if we call it that, then what we've shown on the left is that f of negative 3 equals 0. And on the right, when we call this synthetic substitution, what we've shown is that f of 2 equals 40. It's the same work. It just depends on what we're looking for. And I'd like to take this opportunity to mention that what this illustrates is the remainder theorem. And the remainder theorem states, this is very generally, that if you are given a function, I'll call it f of x, and a constant, which I'm going to call c, with that if, the remainder theorem states that the remainder when that given polynomial is divided by x minus this constant, the remainder is always going to equal the value of f of the constant. So the remainder for our division equals f of the value given here. Now that is really helpful in quickly doing these problems. When, for number 12, we're asked to find the remainder when f of x is divided by x minus 2. We're trying to find the remainder of that. Well, according to our experience with you just talked about and the remainder theorem, the remainder of this is going to be the same value as f of 2. So, if f of 2 equals 15, that means the remainder when f of x is divided by x minus 2 is also 15. I'm going to drop down to number 14, only because I have space. Here the question is x minus 4 a factor of f of x? And that only means that if it is a factor, f of x divided by x minus 4 has a remainder of 0. And in this case, it would also mean that f of 4 equals 0. So that's the question. And let's look. F of 4 equals 7. So I'm going to come back here and change this. If f of 4 equals 7, that means the remainder when f of x is divided by x minus 4 is also going to be 7, which means no. X minus 4 is not a factor of f of x. Now I'm just going to erase this and let's look at problem 13. We're wondering, is x plus 3 a factor of f of x? And that, if the answer is yes, and once again it's a question, that means f of x divided by x plus 3 would have a remainder of 0. It also means that f of negative 3 would equal 0. And if we look, f of negative 3 is indeed 0. So since f of negative 3 is 0, the remainder when f of x is divided by x plus 3 equals 0, that means yes, x plus 3 is a factor. Okay, the very last little piece here. We're wondering if 2x minus 1 is a factor of f of x. Well, that just means that if we divide f of x by 2x minus 1, we will get a remainder of 0. And when I look at something like this, I am way too lazy to do long division. So instead of long division, I am going to reconfigure 2x minus 1 so it is a binomial with a single linear term, so I can use synthetic division. So here is my division problem. And if I want to have divide by a single linear term here for the x, that means I'll have to divide or factor out a 2. So if I factor out of 2 from each of these, I'll have that. Now, you know fractions, if we want to divide the 2 out, then we're going to have to divide the 2 out of here, and so they reduce. So we're going to have, if we factor a 2 out of the numerator, there we go. So now we're taking that fraction and we're reducing it by dividing the numerator and denominator by 2. And now we're going to take x to the third minus 2.5x squared minus 14 plus 7.5 divided by x. Whoops. We're going to divide it by x minus 1/2. And if the remainder is 0, then the answer is yes. So let's look at what we have. Well, there you go. The remainder is 0, so therefore when we divided by x minus 1/2, that is, we can see that it's a factor of this, so 2x minus 1 is a factor of f of x. And for the very last one, we've got zeros of negative 1 and 7, and that means that we have factors of x plus 1 and x minus 7. So let's do some division. Let's first divide by x plus 1. And we hope that that is a factor, and let's take a look at it. There you go. X plus 1 is a factor because the remainder is 0. Now let's divide by x minus 7. Oh, I'm slow at subtraction here. That would be 29. There we go. So now we can see the last, we have a trinomial here. It's x squared minus 4x plus 29. And we wonder, can we factor that? So go back to your algebra, well, it would be spring of algebra 1 or all of algebra 2. If you're factoring that quadratic, we would only have this choice. And notice no matter what the signs are for 29 and 1, we would not be able to get negative 4x. Therefore, the last factor of h of x is x squared minus 4x plus 29. And there we have h of x in factored form. And the last thing we need to do is find the zeros that go with that quadratic. So let's use the Pythagorean, or sorry, let's use the quadratic formula. So x equals minus b plus or minus the square root of b squared minus 4 times a times c all over 2a. So x equals 4 plus or minus the square root of 16 minus 116 all over 2. So x equals 4 plus or minus the square root of negative 100 over 2. So that would be 4 plus or minus 10i over 2. So the last two zeros are 2 plus or minus 5i. And I'm just going to go up here, 2 plus 5i, 2 minus 5i. There are all of the zeros. So thanks for paying attention. I hope this helped. Bye.